Hi everyone, I'm Wang from Hong Kong University of Science and Technology. In this talk, I will present our work towards domestic network transport for distributed DNN training. Deep learning and deep neural network, or DNN, empowers a wide range of AI applications, such as face recognition, automatic driving. Recent emerging of large language model also support famous applications such as ChatGPT. Behind this application, the driving force are powerful and efficient DNNs. However, training DNNs can be very time-consuming with the increasing of model and their size. For example, training bird-based model costs 4 days on 16 TPUs, where it takes 1.7 million GPU hours with A100 per training llama Q. Today, a widely used way to accelerate DNN training is to use data parallelism. The basic idea is to partition a data set into mini-batch and perform parallel training on different workers simultaneously. Note that data parallelism is also well used in recent large language model training, for example, Zero and FSDP. So in this paper, we focus on the case of data parallelism. However, linear scale-up is not the case in practice. Let's take a look at 2 examples. The left figure shows linear scale-up with more GPU within a server, and performance decreases when approaching multiple servers. The right figure gives more direct relation between flops per GPU and the GPU number. As the number of GPU increases, computing efficiency actually decreases. This is mainly because communication cost prevents a linear scale-up. To solve communication overhead, a direct solution is to reduce traffic volume from the application layer. Gradient specification and gradient quantization are widely used by algorithm designers. The basic idea of gradient specification is to reduce the number of gradients, while the basic idea of gradient quantization is to reduce the size of each gradient. However, we found that reducing communication volume doesn't always eliminate the problem. Please note that tail FCT decides the final communication time for the end-to-end DNN training. We use NSDI simulate the communication process of training ResNet 18 with Chinese server. We can find that where average FCT improves, tail FCT remains high. The main reason is that packet loss in transformation timeout. This calls for a network transport solution for DNN training jobs. In the following of this talk, we will refer to network environment for running training as AI-centric networking. iSING must take care of grid failure, since fault tolerance and reliability are crucial for distributed training, especially for large models. Previous work observed that performance downgrading in data center network is often caused by subtle and undetectable failure. That is grid failure rather than full-stop failure. For example, a typical grid failure is the persistent yet hard to detect packet drop of a network device or link. To design a network transport for AI, we find several domain-specific features of distributed training. The first observation is that DNN training process is boundary loss tolerant. These 2 figures show that limited random data loss does not impact the training process. The insight behind boundary loss tolerance is that SGD-based DNN training is essentially an approximation algorithm which estimates better parameter based on gradients calculated from mini-batch. Previous work also showed the robustness of SGD in facing of loss. Such boundary loss tolerance feature inspires us to design a semi-reliable network transport, which can safely cut long tail and maintain the application requirements. Traditional transport, for example, TCP taxed on reliability, were less efficient, while UDP is the opposite. Meanwhile, we can tolerate the slice packet loss due to the above-mentioned grid failure with such boundary loss tolerant feature. The second observation is that using different gradients may generate different impacts on modern convergers. From magnitude-wise, larger gradients are more sensitive to loss. From layer-wise, back layer gradients are more sensitive to loss. As we just did, but in terms of magnitude-wise impact, large gradients are more important, thus less tolerant than small gradients. In terms of layer-wise impact, front layer are less important, thus more loss tolerant than back layers. The reason is that with per-train, the front layer extracting low-level features are generally well learned, thus need few updates than back layers. A difference in gradients inspires us that when Q builds up, we can parallelize front layer gradients over back layer gradients to speed up training pipeline. When buffer overflow, selective dropping front layer gradients over back layer gradients, small gradients over large gradients to maintain model convergence. The third observation is that, unlike many other applications, packets in DNN training can tolerate out-of-order delivery. This is because in DNN training context, the message is just a gradient or parameter, which is typically represented as a 32-bit floating point number. Therefore, multiple messages can be packed within one package, and packet can be processed independently. Meanwhile, the traffic flow in DNN training is predictable. To enhance communication efficiency, DNN training framework divide answer into buckets. For example, the default maximal packet size in PyTorch is 25 megabytes to better overlap communication with communication. BadPS implements tensor partition with default size of 4 megabytes. Such predetermined maximum bucket or partition size facilitates tensor construction at the receiver side, since we can set a predetermined size buffer. This feature of DNN training workload inspires us to break the trade-off using packet load balancing without worrying about out-of-order issues. Based on the above observation, we propose 3 key ideas of MLT. Based on boundary loss tolerance, we can cut tail latency with a semi-reliable transport. Based on a difference of gradients, we optimize We can optimize training efficiency with gradient-aware training and dropping to improve model convergence and speed up training pipeline. Based on the gradient independence, we enable packet rebalancing based on packet level order independence to maximize network optimization and minimize false faults. Here is the design overview. First, data traffic is spread out onto multiple paths on a per package basis to minimize hotspot. Then, if hotspot arise, MLT perform priority queuing, followed by selective dropping in case of buffer overflow based on gradient importance. Finally, if packet drops, which may potentially trigger timeout, as a final one, MLT enables bounding loss tolerance data transmission to avoid long retransmission delay by safely tolerating this packet loss. Here we introduce our semi-reliable transmission strategy. Initially, MLT synchronizes crucial data among nodes, including loss-tolerant bounds and tensor specifics. Transmission from sender stop once the MLT receiver indicates that enough data has been received. If the receiver still lacks data after a full transmission run, the sender check back with from signal. Based on the receiver's feedback, note that we will use a bitmap method in the receiver. Animating packets are sent. On TCP, MLT employs minimal read control and uses a reliable channel only for crucial control packets. For example, the initial information data and such signal. For priority queuing, it maps packets of front layer to high priority, which speed up the training pipeline. For selective dropping, it decides whether to drop a packet from two dimensions. On layer level, we selectively drop from layer packets. The corresponding higher priority queue are set with lower dropping threshold. Note that there is no need for complex deep packet inspection, and both priority queuing and static dropping can be readily implemented with committed switch by checking DICP and iSING fields, respectively. We build a MLT prototype and integrate it into popular ML frameworks. MLT is implemented as a middle layer running in user space between ML framework and the software interface. We provide several of universal communication interfaces that can be integrated into various ML frameworks and distribute the training middleware system, for example, Remote and Backflex. Here is a setting of our test bed. We build an ML prototype with Manlogs, VMA, and commodity switch, and integrate it into popular ML frameworks. Our test bed has 8 physical GPU servers each, with 8 RTX 3090 GPUs, 2 Mellog's Connect X5 NICs, and 4 Mellog's X2100 switches. It forms a leaf span topology with 1 span switch and 3 leaf switches. In physics, each leaf switch have two 100 gigabytes per second link connecting to the spine switch. Thus, logically, we have two spine switch. The 3 rack contain 233 GPU servers respectively. Each server has two 100 Gbps links connecting to leaf switch. We further divide one physical switch into 8 local containers, each with 1 GPU, 10 CPU cores, 32 gigabytes memory, and 25 Gbps virtual mix. The vanilla ML framework includes TensorFlow, PyTorch, and MXNet. Now we show the experiment results. Figures show performance of MLT over baseline and BPS on 4D model using TensorFlow on the PS. From the figure, we make the following 3 observations. First, MLT performed the best of all models. Second, the improvement of MLT become more significant as the number of workers increase. Third, MLT achieved more speedup in VGG16 than other models. The reason is that VGG16 has the largest computation ratio. Figure shows the performance of MLT over the baseline and the BPS in PyTorch and MXNet by training VGG16 and the transformer. Note that the native PyTorch distributed data parallelism does not support PS, so we use the modified version as the baseline for PyTorch. The experiment shows that MLT delivered resistant performance improvements for different ML framework. We also performed a large-scale simulation with 2-core 9Q1 switch and 144 hosts and compare MLT with different transport. MLT also achieved performance. In conclusion, we propose MLT, a domestic network transport for AI-centric networking with floating and spatial properties of machine learning. MLT consists of 3 key ideas. 1. Quantity loss tolerant data transmission based on the loss tolerant feature. 2. Gradient aware packet queuing and dropping based on the different impact of gradients. 3. Order-free packet load balance based on inter-packet order independent. Thank you for your lesson. For more detail, please refer to our paper or directly contact me. Thank you.